So I am delighted to introduce you to Dr. Hausi Muller, a professor of University of Victoria in British Columbia, Canada. Hausi Muller is a professor of computer science there at University of Victoria. He was Associate Dean of Research, Faculty of Engineering for 10 years from 2009 to 2019. He's co-chair of the IEEE Future Directions Quantum Initiatives, and I hope he can tell us about this quantum initiative. I want to tell the audience that IEEE Future Directions has different initiatives who may become in societies or who are serving in the edge of technology. So quantum initiative is one of them, and serves on the IEEE Conference Committee. He's the general chair of IEEE Quantum Week. This year it was held in last October, and he has been also a chair during 2020. It was the first IEEE Quantum Week. So he was vice president of IEEE Computer Society Technical and Conference Activities Board for 3 years, 2016 to 2018. He has been member of the Computer Society Board of Governors, 2015, 2017, and chair of the Computer Society Technical Council on Software Engineering for 4 years, 2011 to 2015. With his research group, he collaborates extensively with industry as an international expert in software engineering, software evolution, quantum computing, adaptive systems, IoT, and intelligent cyber physical system. He is a principal investigator of an IBM CAS project on quantum problem solving and algorithm design on the IBM quantum platform. He's a principal investigator of NSERC collaborative research and training experience grants on quantum computing and dependable Internet of Things application, respectively. As part of the British Columbia quantum ecosystem, he teaches graduate and undergraduate courses on quantum algorithms and software engineering. Hausi, we are proud to having you in sharing your knowledge in Urucon. Thank you, and the floor is yours. Go ahead.
Thank you very much, Professor Sotelo, for inviting me to Urucon 2021. I'm very excited to be here. I would love to be in Montevideo today, but we are online. So very excited to talk about hybrid quantum classical computing challenges and opportunities. And my goal for today is to invite everybody on this journey into quantum computing. We are still somewhat in the early days, but I hope I will convince you today that everything is ready for you to join, regardless whether you never heard of quantum computing or just are here out of curiosity, whether you're in industry looking for quantum computing applications, for example, or whether you're a student and deciding how to get into quantum computing, because there seems to be a lot of jobs in this area, or like Professor Sotelo, creating startups, entrepreneurship opportunities for the local quantum ecosystem. That's my goal for today. So let's get started. So we'll talk briefly about what is quantum computing, how did we get here, hardware and software roadmaps from the major companies, and then talk about hybrid quantum classical computing. That's the name of the game right now, and in particular, how to integrate high-performance computing and quantum computing. So if you have people from supercomputing centers here, they will hopefully get a lot out of it. Quantum runtimes and intermediate representation, that's the way to facilitate these days hybrid quantum classical computing. And then finally, briefly, we'll mention Quantum Week, since I'm general chair of that right now. And hopefully you can all participate next year. And hopefully that will convince you to write the quantum computing program tonight. It's doable. You can do it. All right. So what is quantum computing? It's computing using nature, atoms, qubits, superposition, entanglement, and interference. So these are sort of the core components of quantum computing. How powerful is quantum computing? It's incredibly exciting because it is the only technology that we know of that could fundamentally change what is practically computable, and this could soon change the foundations of chemistry, material science, biology, medicine, and agriculture. There's a famous quote now by Fred Chong, University of Chicago. And here you can see the power of quantum computing. We are not there yet, but we are getting there rapidly. So in a classical algorithm, what takes for certain problems, really hard problems, can take years. That can be done on a quantum computer in minutes. And you can see the speed up is absolutely dramatic, exponential versus polynomial time. So that's what we are aiming for in part, and that's typically referred to as quantum advantage. Once a quantum computer can outperform a classical computer, if you like. Having said that, there will never be just pure quantum computation. It's always a combination of quantum and classical computation. And that's what we talk about today as well. So quantum computing, how is it so powerful, if you like? Well, on the one, the really key idea is to put all these qubits into superpositions. So here we have this, let's see whether we can get a cursor here. Now we have a pointer. These are the qubits here. It's like a musical score. And a qubit here executes, if you like, from left to right. And the cool part is that all these qubits execute in parallel from left to right. And here are just 4 qubits, but IBM just announced machines with 127, a chip with 127 qubits. And this is a very famous circuit. It's a teleportation. No, not this one. Next one, I guess. So you put the quantum computer into superposition. Then you have a whole bunch of computations here in the middle, including entanglement. And then finally, kind of undo the superposition and measure. That's sort of the classic high-level overview of a quantum algorithm. And at the end, you just have a single result. So we go from this, where you have lots and lots of possibility, to just one solution. And there's a lot of parallelism involved, and that's how you get the speed up. Another way of a really nice little explanation by Chris Ferry, readily accessible, explains exactly how this all works. Superposition, compute, phase manipulation if needed, and then at the end, uncompute, and then you measure. And in lots of different applications, we want to iterate over this in the middle. We don't necessarily want to go all the way back to classical computer, and that is possible with runtimes these days. This is the circuit I was looking for. This is the teleportation algorithm. Very simple algorithm, very, very important algorithm. And so these single lines here are qubits. That's the musical score, if you like. And these are classical bits, just 0 and 1. But these qubits can be anywhere between 0 and 1 with respect to a real number. Anyway, that's what it's all about. Where does this come from? Well, this is actually how nature computes. There's a very famous quote by Richard Feynman from around 1981, where he challenged the physics community to actually come up with a quantum computer. And he says, nature isn't classical, and if you want to make a simulation of nature, you better make it quantum. Then you can do it maybe accurately. So far, we do a lot of simulation in chemistry, but it's all approximations, if you like. So all these beautiful pictures here on the left, there's a lot of quantum computation going on everywhere. The magical story of quantum applications. What if we had this quantum computer this powerful computer, what kind of applications could we actually do? Well, here's a little example from Maggie Lee. We have this annual workshop at the IBM CASCON conference, and we had that like 3 years ago or 2 years ago. Was all of a sudden this person, Maggie Lee, came up to me when I was chairing the session. I was asking for the people who actually talk in the next session. Maggie Lee came up, and then I said, how can I help you? And she said, well, I'm the next speaker. Oh, okay. And she turned out to be a high school student, just 15 years old. But here's the story of Maggie. She learned 5 years earlier, around the age of 10, that her mom was diagnosed for cancer. And then Maggie started to research applications, cures, medicine for cancer, and figured out that it takes a very long time to come up with drugs, 20, 30 years to get it approved. And maybe that has changed by now, but she then figured out maybe quantum computing helps, and she studied quantum computing hard over the next 5 years, and by the age of 15, she gave really terrific talk at IBM CASCON in our workshop. So that was the best talk, very exciting, great simulation for everybody. And now she's giving lots of talks, particularly to high school students, to entice them into quantum computing and some of our other workshops. All right, and here's the spectrum of applications that quantum computers can address, basically everything, if you like, but there are sort of key areas, the ones that are highlighted in the middle. Problem types. One is simulation of nature. We get to that in a second. The other one is optimization, and there are many, many optimization problems, hard optimization problems, and machine learning. So these are sort of, if you like, low-hanging fruits, the short-term applications that are being targeted even as we speak. Cryptography here on the left is also very important, and in part that's why governments invest a lot of resources and a lot of funding into quantum computing these days. Everybody wants to get there first. So this is a headline from the 1Qubit website, the company in British Columbia, where I am, and redefine intractable. Intractable problems are hard problems in computer science, and they have this exponential behavior, and trying to figure out ways of making them practical, these algorithms, that's one of the key goals. So there are two big quantum computing promises. One is solving classically intractable problems faster. And the second one is simulating nature or simulating physical systems like molecules, like particles in physics, and so on. There are lots and lots of applications, and quantum computers are particularly suited to simulating physical systems because that's physical systems, like molecules, behave quantumly, if you like. There's a nice little talk on by Ulrike Steger, one of our faculty members, and that is part of this BC quantum ecosystem, where we have regular talks, and this is building blocks. Her research is building blocks for intractable algorithms. All right, so don't throw out your laptop yet. You will always need your laptop. That's very important to realize. Quantum computers will not replace classical computers. So we will have integrated quantum and classical architectures, algorithms, platforms, and so on. That will be the norm. For quantum advantage, somehow, for a quantum computer or a quantum classical computing arrangement to outperform just a traditional classical arrangement, we need to figure out how to arrange superposition, entanglement, interference, and how to do that in such a way that we can take basically use the best parts of classical computer and the best parts of quantum computer and put them together in the right way, we show you some ways today, then we might have quantum advantage. For certain small problems, we are actually there with quantum, can demonstrate quantum advantage, but over the next 2 or 3 years, we will definitely be right in the middle of the journey with respect to quantum advantage. And it's not a single point where you achieve that. It's a long, prolonged time to achieve quantum advantage, and we will continually improve the advantage over classical solutions. All right, how do we get there? Well, at first there was quantum mechanics and quantum mathematics, if you like. There's a rich history of pioneers, famous thought experiments, and we just celebrated the 40th anniversary of this Physics of Computation conference that was held at MIT with IBM in 1981, when Richard Feynman challenged everybody. And a couple of years ago, the National Academy of Sciences, Engineering, and Medicine in the US published this report. It's a nice book, highly recommended. You can buy it, but it's free. You can freely download it as a PDF. You can easily find it if you search for it. Highly recommended. It gives a relative conservative assessment of the state of quantum computing like 2 or 3 years ago, but it will help you understand the field as a whole. So then now, basically, all the major companies have released roadmaps. We'll see some of them, and that gives a good idea what's possible, what they try to achieve over the next decade. The appetite to learn about quantum computing has increased dramatically over the last 18 months, I would say, or 2 years. And we are well now on our journey to quantum advantage. And yes, I'm very proud that we created Quantum Week. I'm the founder, and that has taken off like gangbusters with 1,100 people for 2021. So these are some of the pioneers. I can't go into detail, but it's very important to appreciate that this really took place 100 years ago. And then it came sort of to a grinding halt around 1935 with the so-called EPR paradox, Einstein-Podolsky-Rosen paradox. Einstein just questions the power of quantum computing. He had trouble wrapping his head around it, and then it came to a grinding halt, and till Bell's inequality was proven in 1964. In the meantime, von Neumann, he was also in the middle with all these folks there in the early part of the 1900s to 1926, in there, where they all developed quantum theory. And but von Neumann went to the digital route, and in the end, that's why digital computing came about. But if we wouldn't have had the EPR paradox, maybe we would already do full-scale quantum computing today. Then I mentioned this 1981 conference, and then quantum cryptography with the BB84 algorithm, also from a Canadian, Brassard and Charlie Bennett at IBM. That sort of launched the interest of governments, if you like. Then some really magical results in quantum algorithms, and realizing that error correction will be a big challenge. And then finally, real quantum computers were to be built, and it started kind of with De Vincenzo criteria. And he just gave absolutely fabulous talk at IEEE Quantum Week about the history of superconducting qubits. It was fabulous talk. And now IBM, this is the IBM perspective, if you like, so that's a little jaded, but still we now have commercial quantum computers that people can readily access. So now we get to some of the quantum advantage and where we are. So the foundations are there. We have had quantum algorithms since the mid-90s, early 90s, and with ginormous results and ready to be harvested. this still continues, of course. So I would submit that we are quantum ready at this point, and these are terms coined by IBM. And now we are in this really quest for quantum advantage. D-Wave is one of the first commercial quantum companies. It's from British Columbia, Canada. It's a different type of quantum computing, quantum annealing. And they actually have machines with 5,000 qubits, or SQUID, superconductive quantum interference device. But every qubit is only connected to a handful of other qubits, if you like. So it's limited. So if you can formulate your problem as this very restricted problem to a certain extent, then D-Wave has a terrific solution for you. IBM started with qubits around 2011 or 10, and this is now the history of qubits at IBM. And with Falcon, they made tremendous progress with respect to quality. And here's an interesting diagram. You're all familiar with Moore's law, how we kind of doubled the power of computers every 18 months. But now, for the first time in history, so and you know that this curve is flattening out because we reached the physical limits with respect to silicon. And but now, because of quantum computing, these two curves actually split there at the top, and we actually grow faster. So classical computing is flattening now, but with quantum computing, we can achieve dramatic improvement. And if we wouldn't have had this 1935 EPR paradox that slowed it down, this light blue upper row there maybe would be much further back, much more to the left in history. So it's very interesting, this diagram. Honeywell that has ion trap qubits, and they achieved very high quality qubit. They're the first to get to 64. So very high quality qubits, and made terrific progress, and that surprised many. IMQ is another company that is going startup that is going public, and they're also based on ion trap technology. Google and IBM, they all work on superconducting qubit technology. Here's the roadmap for Google. There's a very nice talk by Hartmut Neven from last summer. You can easily find it, and that's how Google envisions a million qubits down the road. This is the IBM hardware roadmap, and you can see IBM just achieved with Eagle 127 qubit. Google is still in the 70s or so, but I'm sure they come up with 100 qubits, or already have 100 qubits already. So for next year, IBM aims to come up with Osprey 433 qubits. And then once you get to 1,000, you can use a lot of these qubits for error correction. If you have 300 qubits, logical qubits, you can do a lot of computing, probably enough computing for most of us. But it's still a long way till we actually have 300 logical qubits, fully fault-tolerant qubits, and high-quality qubits. This is the arrangements of the qubits and how they are connected. If you want to entangle two qubits that are far apart, like in this diagram on the right, qubit 0 to qubit 52, that's a lot of work, and you have to go through a lot of hops, if you like, and you introduce a lot of noise in the process. But there's lots of software that optimizes entanglement to qubits that are closely connected, like 48 and 52. This is the latest diagram, very similar, if you like, of IBM Washington. That is this Eagle. Eagle has landed with 127 qubit. And this is the software roadmap of IBM. That's a very telling roadmap, very interesting. On the left-hand side, you have the people involved. So at the bottom, you have hardware, and then the kernel developers is just like in a Unix kernel. It's the core of the interface. Then the algorithm developers, a lot of computer scientists work on that. And then model developers, these are the folks for a specific application domain and model their prompts onto the algorithms and then onto the specific parts like runtimes that accelerate the hardware. So now everybody who hasn't written a quantum program, I kindly invite you to do that tonight. And here's how you do it. IBM Qiskit is probably the most common platform, but right behind is Microsoft Azure Quantum, Google, and D-Wave is also readily accessible these days. So all you have to do is basically sign on and come up with a little program. There's lots of help, lots of online little programs you can directly take and simply execute. And then you either execute on an interpreter or directly on a machine. Interpreter is perfectly fine for small programs, and only if you need more than, say, 30 qubits do you actually need a bigger machine. But for education, your interpreters are just fine. However, all these companies, they give you access to real machines. And real machines, they are noisy, and that's the big difference, whereas interpreters are not noisy. But I invite you to check this out. And quantum computing is different. You need a lot of imagination, and you need training in that. If you've been a programmer for many years, yes, you can immediately get on to most of these platforms on the left. They either use Python or Q#, and so on. You are instantly familiar with that. But then to think algorithmically in terms of think quantumly, if you like, then that is a lot more challenging. It just requires practice. So get into it tonight. Qiskit is an amazing platform. It's open source, has a terrific textbook. Actually, there are now 2 textbooks, the old one and the new one. The new one is still beta, but readily available. You can learn all the quantum computing, if you like, just by reading this particular textbook. And you do very well. Microsoft has also excellent textbook, also lots of online material. So doesn't matter where you go, what you prefer. If you are Python expert, start with Qiskit. If you are Q# expert or C# expert, start with Microsoft. IBM has this circuit composer. And by the way, Microsoft just integrated Qiskit because it's open source in their platform. So you can do both Q# and Qiskit on the Microsoft platform. The circuit composer has a bunch of gates at the top. These gates you can drop down onto the circuit being constructed. This musical score, if you see on the left-hand side here, we have qubits and we have classical bits. And when you measure, you generate a value in a classical bit. And there are all kinds of visualizations, how to look at a particular qubit. And then you see what this circuit, what that looks like in actual code in Qiskit. This is a great way to start using this interactive Qiskit circuit composer. Then very quickly, you just graduate to writing Qiskit programs, and the base of that programming language is Python. Qiskit is open source, as I said, but not just the source code, but it's super open, and there are lots of there's lots of open content, open access programs and partners, summer schools, and certificates. And there you can really see the appetite that is out there to learn quantum computing and how it has increased dramatically. One of our students just came home with a terrific result this summer when she attended summer school and at some point was in the top 4 of that summer school of 4,000 people. It was amazing. So what it will take to make quantum computing a practical part of an industry relevant workflow? Well, you need quality circuits, quality programs, if you like, and you need to figure out ways to improve the speed of these circuits, and that will change all the time with hardware and with software, and what variety of circuits can we actually execute. There are some circuits that are quite readily executable right now on the current platforms, and others are a little bit more challenging. It depends on the application to a certain extent. But on all these things, tremendous progress is being made. All right, so now let's concentrate on hybrid quantum classical architectures, runtimes, and algorithms. There's a little paper from 2020 that might give you a good idea what is needed in quantum and classical integration and hybrid quantum computing. It's already a little dated since there's very little described in that paper about quantum runtimes, which I'll talk in a second about. All right, so there might be some people out there working in supercomputing centers or using supercomputing centers. So how are you going to work with a supercomputing center, and how are supercomputing centers integrating quantum computing? This very famous quote from D-Wave from Murray Tom. He had a panel at Quantum Week. He basically advocates already in 2019 that quantum computers promised unrivaled performance for certain types of tasks, solving optimization problems, but it has to be integrating. You have to integrate hybrid high-performance computing and quantum computing. So for strategies for supercomputing centers, historically, they are reluctant to embrace quantum computing. However, now that everything with respect to quantum is in the cloud and supercomputing centers as well, so it will change things. So since we are on the road to achieving advantage, the supercomputing centers have to think about that. And now that all these classical and quantum integration is taking place, you can readily integrate Microsoft Azure Cloud or Amazon clouds, AWS clouds, or IBM clouds these days, and get access to almost any quantum computer there is out there. Amazon, Microsoft cater to different qubit providers or hardware providers, and IBM has their top-of-the-line hardware, if you like. So it's time for supercomputing centers to embrace quantum and to integrate it. It's not an easy process or straightforward process, but it's something that will have to be done wherever you are. All right, so hybrid engineering, what are the challenges and opportunities? It's basically workflow optimizations and trying to understand how to orchestrate the workflow. And here are 5 different strategies. We can they all are around decomposition. Decomposition of the problem, decomposition of the algorithm at hand, decomposition of programs, and decomposition of programs will change over time. So just like in classical computing, if you have a sequential program and all of a sudden you have a parallel computer, you can easily figure out, not easily, but it's doable, figure out how to decompose the program so that a certain chunk runs on a sequential machine or core, and but all these sequential part can be run in parallel. And actually wrote at some point a program to do that for C programs. And then once you get to the circuit level at the quantum side, you can also decompose the circuits. Right now, we can only have limited size circuits, because they decohere after a while. And so we can only write short programs for quantum computers right now. But if you somehow break these circuits up into parts, then you can also execute them in parallel if you like on different chips. And the latest and greatest is quantum runtimes with intermediate representation, intermediate languages. D-Wave from the start had decomposition of the problem. So D-Wave has the advantage to have very constrained problems, optimization problems in particular, where all the parameters are around the diagonal of a big matrix, if you like, then D-Wave is very good. And if you can decompose your problem in such a way that it caters to the D-Wave platform, this is a perfect solution. Another really famous problem decomposition approach is by 1QBit, and both of these companies are from British Columbia. And they are really good at decomposing chemistry problems, molecule simulation problems, use classical and quantum VQE. We'll explain VQE in just a second. And they're really famous of breaking down the problem and solving the problem sort of at the problem side. That has many advantages. That's what variational quantum Eigensolver looks like. It's a particular technique. It's very successful, used a lot in practice classically, and it can be used on NISQ quantum computers, so near-term quantum computers, if you like, quite effectively. And there are many strategies for doing so. So one of the first was IBM to come up with this integration of classical and quantum. Then that's what really took place in the last year or two. We have this notion of parameterized circuits that's also used a lot in machine learning, but it's the same idea. You can use VQE for simulating molecules and for machine learning. And now there's Qiskit runtime, where we have the classical part and the quantum part in very close proximity in upstate New York, where all these IBM quantum computers are located. Well, there's one in Japan and one in Europe as well. But still, Qiskit runtime is now supported on all of these machines. It has many advantages. And now, all of a sudden, we can reorchestrate VQE algorithm, and that's what it looks like now. So we have users that create certain algorithms that can be stored in the quantum Qiskit runtime registry, and then the Qiskit runtime, when it's called for, simply use some of these established solutions, if you like, but also new solutions. You enter them in the queue just like before, but then the classical and the quantum part is executed in upstate New York, if you like. And before, there was a lot of latency going back and forth between the laptop and that. So it reduces the latency dramatically. Yeah, so I have to hurry up a little bit here. But what they've achieved over the past, just in 1 year, 120 times improvement in speed, and that's quite dramatic by doing that. So the runtimes are working really well. It's not new. Intermediate languages have been introduced by Oak Ridge National Lab, as well as Rigetti computing quite some time ago. And now Microsoft has this QIR. Look this up, check it out. Quantum intermediate language, and with that you can build and connect all kinds of quantum hardware and software together. That's how they were able to connect Qiskit and Q#. And so that's quite the ecosystem that Microsoft has built just in 1 year on Quantum Azure. And Google, same way, more sort of service-oriented, but both Amazon and Microsoft are also very service-oriented. And they have their own language called Cirq. And then there are domain-specific optimization problems, but again, then more at the circuit level, you do some optimizations. This is sort of standard compiler rewriting technologies. Just like you have certain instructions, you can rewrite them in different gates, if you like, at the lower level, and that will help you tremendously in speeding up your algorithms. So there are many capabilities that are forthcoming, like dynamic circuits. We hope that they will come in 2022. Gives us lots more flexibilities to parameterize circuits, and so you have to go less to the classical side. So there are all kinds of capabilities that have been invented, like circuit knitting, reorchestrating circuits. And in the end, it's all about scale, quality, and speed. You got to have all three of them to make progress towards quantum advantage, as well as performance and capabilities. And IBM is aiming for this frictionless computing. D-Wave has achieved frictionless to a certain extent already, in the sense that you can just express an optimization problem and just optimization problems at a very high level, and then that is translated with a whole bunch of pre-processing into a program that readily executes on the D-Wave machines. And that's the goal as well with respect to frictionless and serverless programming. So that's the roadmap we can expect from IBM. Is quite exciting, and looking forward to what they have to deliver next year. Actually, these days, yesterday and today, we are running a workshop on the ecosystem in Canada. This is all what's going on. On the right-hand side, these are all startup companies in Canada. On the left-hand side is sort of the government and provinces, how what they do for quantum. It's quite amazing what we compiled. That is currently going on, this workshop. And now a few words about Quantum Week. We kind of found an interesting gap between these academic conferences that have been going on since the early 90s, like QIP, and these industrial summits that emerged by these big quantum companies like Google and IBM, Microsoft, and others, Honeywell, and since 2017. And now we are somehow in the middle. So it's time to close this engineering gap, and everybody is deeply interested in that. Here are some interesting numbers. We had a lot of sessions because we were virtual, 293 sessions, 320 hours of recordings. And you can actually see all these recordings right now if you sign on for Quantum Week on demand. We had over 1,100 registrations. It's just amazing for a conference that has been held the second time. So the interest and growth has just been amazing. But what I observed between 2020 and 2021, the progress among everybody, whether it's supply chain companies or full-fledged quantum companies, software, hardware, everywhere, the progress has been absolutely astounding. If you want to see, read a really good article from my perspective, I'm biased, of course, but there is the Quantum Computing Report, wrote a little report about all the keynotes at all the 10 keynotes at IEEE Quantum Weeks. And we had keynotes from IBM, Microsoft, Honeywell, and Google, and so on. And if you go read this report, and there was quite a few controversial things in these keynotes, you get a good understanding in just a few pages here from the Quantum Computing Report, what the state of the quantum industry is all about. Highly recommended. You can easily find it using Google.
Hausi,
yes.
excuse me one interruption. I want to highlight to the Latin American attendees that a special registration
It's
fee
coming up.
was... okay, so I
There
want
we
to...
go. Now you can say.
Okay.
Say it. It says Professor Rafael Sotelo at the bottom. Go for it.
Okay. So it's a special member pricing for IEEE Quantum Week. There has been, as you can see here, so it was spontaneous from my side. So thank you for bringing this. I was very keen. I will tell this in Spanish, so as most of the people gets it. Estimados, esta conferencia, este es un aviso de que esta conferencia fue en octubre. Allí como ven, del 18 al 22 de octubre de este año, se hizo en octubre también del año pasado. Como recién veían que estaba Hausi comentando, más de 1000 personas se registraron. Es el evento más grande de computación cuántica en el mundo. Hubo unos precios especiales para miembros de IEEE de región 9, o sea, de América Latina y el Caribe, para miembros y no miembros. Allí ven, desde 15 y 25 dólares. Esto es una abismal ventaja para nosotros, que a veces asistir a conferencias de cientos de dólares, el registro normalmente era unos 400 dólares. Entonces, esto es un aviso, y un aviso para el año que viene, estar atentos y pedir que se repita. Ahora se lo voy a pedir en inglés. So, thank you, Hausi. I think I gave the idea, and we hope this can continue next year, because for people from Region 9, IEEE Region 9, I mean Latin America and the Caribbean, it is very difficult in general to register for the full fees that in general are very expensive for our region.
Yeah,
thank you.
I totally appreciate that. But I also want to point out it's still available, right? You can watch 320 hours of programming from Quantum Week 2021 and highly recommend it. Whether you are an expert or a beginner, you have tutorials and you have workshops on lots of different topics. And here's the overview. And also, Professor Sotelo, he orchestrated this quantum entrepreneurship workshop. I highly recommend it. So if you want to be a quantum entrepreneur, have the ambition to create a company, go watch this workshop and then connect with Quantum South team. How is that, Rafael?
Thank you, Hausi. Yes, please contact us.
All right.
Yes.
So that's what the online platform looks like. It's actually very nice, easy to use, and has worked very well for us. And the next conference will be in September 18th through 23rd, so a month earlier than this year. And currently it's scheduled as a hybrid event. Hopefully we'll still have a good attendance in person, but also virtual participation. So that's the goal. Will we know more around March time what actually it looks like given the pandemic. So a couple of take-home messages. That's almost the last slide. So the appetite to learn about quantum computing has increased dramatically. Quantum computing is now beyond what can be simulated classically. With a 127 qubit machine or 70 qubit machine, you cannot simulate what you can do with up to, say, 30 qubit interpreter. Hybrid quantum classical computing to achieve quantum advantage, that's the norm now. That's the way to go. And it's time to invest in that, regardless whether you're in a supercomputing center or whether you're teaching it. It's very important. I can only recommend to engage, everybody should engage in their local quantum ecosystem. And quantumsouth.com is a outstanding one, just received awards. And explore quantum runtime models on multiple platforms. That will be very versatile for you. Explore quantum applications for your business. Try to concentrate maybe first on optimization problems. There you get the most bang for the buck right now, but also machine learning if you're interested in that. And if you're interested into simulating molecules, that can be done right now. Identify business challenges. Right now, in your business where quantum computing may offer a competitive advantage. It's important to wrap your head around that. You won't gain that overnight, so it takes time. And then explore Quantum Week 2021 on demand, and please engage in Quantum Week 2022. So thank you very much for inviting me. And I would like to thank our big team, also from ICESI University in Colombia, where Nora Villegas is Dean of Engineering, and I think she's on the line. So thank you, Professor Sotelo, for inviting me. Thank you, everybody, for attending.
Thank you, Professor Hausi Muller. Thank you, Hausi. Thank you very much. Very interesting talk, and I think your message, engaging your local quantum ecosystem, it's an excellent one. So we are open to receive interested people to work on here locally, and I hope we can interact our ecosystems. British Columbia is an example for the world on how is this pushing quantum computing. So we have 2 questions from the floor. I challenge you to answer it in 1 or 2 minutes each one. So the first one is from Jefferson Jalico Tapia. It was made at the beginning of your lecture. Professor, what would happen in the future with the current level of cryptography if we use a quantum computer?
Yeah, it's a very good question. And that's why all the governments are deeply interested in quantum computing and investing in it heavily. So the promise is that you can basically break the codes with 250-bit encryption eventually. And eventually it's probably 10 to 15 years off still till you can do that. But whichever government is first to actually do that probably has some kind of advantage, if you like, and that will come. So the other coin is that it's time to invest in quantum encryption, and that can be done right now. We had several companies in that domain at Quantum Week sponsoring us. Quantropy from Ottawa in Canada is one of them. There are lots of different opportunities for doing that. And telecommunication networks, they have to do that rather sooner than later. How is that?
Very well, thank you. And the other one is more technical, I think, beyond the quantity of qubits. Beyond the quantity of, was written when you were talking about the quantity of qubits and the quality. When will the qubits have the quality that allows us to implement algorithms such as Shor's algorithm or the quantum Fourier transform? This is from Laura Gatti from my team from the university and in Quantum South.
Thank you very much for this excellent question. So the number of qubits is just one measure, but the quality of qubits has several components, and that's really important to realize. Also, there are different flavors of algorithms. For Shor's and Fourier transform, you need quite high quality qubits, and at this point with 127 qubits, and if you can break that down in sets of say 30 qubits, you can already have tremendous algorithms or search spaces you can explore. So that's perfectly doable. But there are other algorithms where sampling is involved, or Monte Carlo algorithms and techniques. There, the quality of the qubits is not as important as for Fourier transform, for example. So it depends on the application. Sometimes noise is actually helpful, and sometimes it's not helpful, and the quality has to be super exact.
I see. Okay. Well, Hausi, thank you very much for your support to IEEE Urucon, and hope to see you soon here in Montevideo. And once again, thanks to your hard work with Quantum Week, which has excellent results for all the worldwide community. Thank you very much. We will clap hands at home for you.
Thank you very much, Rafael. I really appreciate that you invited me, and I wish all of you a wonderful UruCon 2021 conference.
Thank you very much. Thank you very much. Well, with this, we end this session. Thanks to all of you. Thank you, Hausi. Bye-bye.
Bye-bye.